Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also helps us reach others who want to test their math skills with these types of test questions. So this will be our 27th part in our math skill series, and we got a whopper for you here. So this is going to be a very long one. So what we have going on is that we have to determine the area in the blue region shown here on this left. And we are told a bit of information. So we have this portion from A down to D. If I scroll just a little bit here, we have this portion. Well, come on, work with me. There we go. So we have A to D here, which is 75.1169 millimeters. We have this portion from D to C, which is 129.8347 millimeters. We have this red line going all over the place. Well, this red line is of an equation such that the following is true, that you would have dy dx is equal to 1 plus y squared over x squared, which it has a boundary condition of y of 1 is equal to 0. So I'll talk more about that a little bit later, but let's keep reading. And then we have A to C is the diameter of this semicircle shown here. EFCB is a rectangle. The equation that makes this differential equation true ends at point F. Points E, B, and D align vertically. And the equation considers that A is such that the XY coordinate system is the origin point at 0, 0 at point A. And the equation crosses point B at y equals 0. So this is set up in such a way that A is my origin point. Thus, AC is my x-axis. Everything above this point will be considered as y as positive. Everything below this point is considered y as negative. So this equation of y that represents this red line here, which as it's shown, it just skyrockets here, goes all the way back down negatively, and then slowly comes back up and then rises up to F. There's a y equation that makes this differential equation true given the boundary conditions. So what we're going to have to do is we're going to have to split this problem up into two portions. One dealing with the semicircle and the triangle there, and then the other dealing with the rectangle and the differential equation. Now, they are all interconnected here because if we find the area of our rectangle, we will need BC. Well, how do you get BC? Well, to get BC, you're going to have to work with the semicircle and the triangle. You're going to have to use this differential equation here to get what value the differential equation or the y equation is at point F to get the height of the rectangle. So a few things that we're going to need. We're going to need AB and BC, as I just said, and we're also going to need FC. AB, BC will be found using the triangle and the semicircle. FC will be found utilizing the properties of BC and AC along with the differential equation. So let's start with the semicircle first, because we're going to have to get some dimensions down here in order to work with the differential equation. So we have to start with our semicircle. So let's scroll down here. And here is a blown up portion of the semicircle. So we were told in the beginning that AD is 75.1196 millimeters, and CD is 129.8347 millimeters. And you're probably wondering why such nasty looking decimal point numbers. Well, you'll see why here in a little bit because the numbers actually come out a little bit nicer with these. So what do we go with here? What do we do? Well, we do need the diameter. Once we find the diameter, we can use the overall information that we have, and we can find what AB is, and we can find what BC is. The main goal is to get BC over here. So how do we utilize this? Well, what we can use is the first theorem, which will be Thales' theorem, and I believe I am pronouncing that correctly. So Thales' theorem states that if you have 2 points of a triangle that align with the diameter of a circle, meaning that we have A and we have C over here, and they connect to a third point that is along the circle's edge, which would be point D. The angle that is forming at the circle's edge point, which would be D, will always be 90 degrees. So anytime you have a triangle that is inside a circle like this, or inside a semicircle like this, if two of the points align with the diameter of that circle or semicircle, the third point along the circle's edge will always be 90 degrees. So what we have here is a right triangle forming, and we have two sides of the right triangle. We just need the third side, which is the hypotenuse side, which happens to be our diameter. So what we can do is that we can use the Pythagorean theorem to find our diameter. So it would be d squared is equal to 75.1196 squared plus 129.8347 squared. And then you just take the square root of that right side, and d pops out to be 150 millimeters. Oh, there's our nice number showing up. So if our diameter is 155 millimeters, our radius then would be 75 millimeters. So why is that important? One, I just told you that we can use this to find BC, which is the width of our rectangle. How else would we use the diameter? Well, if we scroll back up to the main picture, we're eventually going to get a y equation for this curve. And we are told that A is our 0, 0, our origin point. So what we would have to do is that we would have to plug in an x value, which would be AC, which happens to be our diameter. So if we plug in 150 millimeters into this y equation for x, it will give us the y value up here at F, which just happens to be the distance from F to C, since B is crossing right here at 0. But we're not there yet. We're still working down here. So let's continue to work here, and let's try to find BC. Well, how are we going to do this? Well, let's go ahead and let's split this right triangle up into a couple different triangles. So we were told that B and D align vertically. So what we can do is we can draw a straight line down from our diameter line to point D, and this would actually form a 90-degree angle since it aligns vertically. Well, can we really find anything there? Not really. So let's work on a different triangle here for the meantime and come back to this one. So let's set this as our center of our circle. So that means that this dimension would be our radius r, and then from A to that center would also be r. And let's also connect in from D to the center of our circle here. Well, what would we have here from A to our center to D? Well, this would be our radius r. A to this point would also be r. So our triangle would look something like this, where this would be A, this would be our radius r, which is 75 millimeters. This down here would be D, this would be 75 millimeters, and this would be 75.1196 millimeters. Okay, so how does that help me get A, B, or BC? I really don't know. Well, look at it this way. This angle right here at angle A will be the same for the triangle ABD as for this triangle right here. Let's just call it alpha for right now. So if we can find alpha for this triangle, it will be the same for the right triangle of ABD. And since this is a right triangle, if we know one side and one internal angle, we can find the remaining sides. So we could find AB. And thus finding AB, what we can do then is that we can subtract that from the diameter and get BC. So let's go ahead and do that. So how would I find alpha? Well, we can use the law of cosines to find alpha here. Oh, that's not how you spell cosine. So the law of cosines, we would have 75 squared is equal to 75 squared plus 75.1196 squared, subtracting off 2 times 75 times 75.1196 cosine of my internal angle alpha, keeping in mind that this 75 over here is this portion squared on the left-hand side of the equation. So we would just have to rearrange and solve for alpha. And rearranging and solving for alpha, we get this. So the 75 squared on each side will disappear. They'll cancel with each other. So we would have cosine inverse of 75.1196 squared divided by 2 times 75 times 75.1196 And then my alpha will pop out to be, my angle is 59.947 degrees. Alrighty. So we have found our angle here, and then what we can do is we can utilize that with our right triangle of ABD, where this is A, this is B, this is D, and we know that this is 75.1196, and we know this angle is 59.947 degrees. So we're looking for AB here. Well, AB would just be 75.1196 times the cosine of 59.947. And that would give me a side of AB equal to 37.61967 millimeters. And there's a reason why I'm taking it out that far. You'll see why. So now with AB known, what I can do is just take that and subtract it from the diameter, and then I can get BC. So BC would just be 150 millimeters, subtracting off AB. And then BC will give me 112.38033 millimeters here. So what I have found is I have found my dimensions for my overall diameter, what I plug in to my original y equation that I'm going to have to find. And I've also found my width of my rectangle, which is 112 with a bunch of decimals to it. So why did I find AB? Why couldn't I just use that left side of that, or that right side of the triangle to find BC first and just leave AB out there? Well, you'll see why. There's a reason why I found AB, and that will be coming up later. So AB is somewhat required. So before moving on to the differential equation, let's go ahead and let's find the area in blue for the semicircle here, because we're going to need it. So what we're going to do is we're just going to find the area for our white triangle and subtract that from our overall area for our blue semicircle. Well, my triangle area, since it is a right triangle, will just be 1/2 times my base and height, which would just be my original given dimensions of 75.1196 multiplied by 129.8347. And this gives me a total area for that white right triangle, say that 5 times fast, of 4,876.565 millimeters squared. Alrighty, so then the area of my semicircle, well, that's not how you spell semicircle, there we go. Of my semicircle, the total area would just be pi r squared over 2. So this would just be pi times my radius squared, which is 75 millimeters, over 2. And that gives me 2,812.5 times pi millimeters squared. So the remaining area in blue inside of the semicircle will just be this. So area in blue for the semicircle, and that once again having trouble spelling semicircle, would just be the 2,812.5 times pi, subtracting off the 4,876.565, and that would give me a total area remaining of 3,959.164 millimeters squared. So what we're going to have to do is find the overall area for that blue triangle or blue rectangle, and then add this to it. So I'm just going to put a big old arrow there because we're going to have to find this later. So far what we've done, just to recap, we have found the area in blue for the semicircle. We still need to find the area in blue for the rectangle. We have found the overall diameter for the semicircle, which would be my coordinate system for this X point that I will need. And I've also found BC, which is my width of my rectangle. The only thing remaining is F to C. Once I find F to C, well, I just multiply it by my width, add it with the number I just found. So now comes the difficult part, which is the differential equation. This thing looks like it could be easy, but I trust you, it's not. Or trust me, it's not. It's very long. And there's a lot of substitution involved. So what we're going to have to do is we're going to have to find a y equation. And it's going to be a long y equation such that this expression is true. And this y equation, all we're going to have to do is find it and then plug in our diameter. And that would give us what, or plug in our diameter for a value of x. And that will give us the value of y up here at f. So let's start working on the differential equation portions here. So what I'm going to do is I'm going to scroll down and I'm going to rewrite the differential equation and start working with it. So let's go ahead and let's just do it in black. So we have dy dx is equal to 1 plus y squared over x squared with a boundary condition of y of 1 is equal to 0. Alrighty, so here we go. Switching gears from geometry to differential equations. So the way I'm going to try to solve this is by separation of variables. It's one of the easiest processes for differential equations. So separations of variables is where you get all your variables of one type on the left side and then all the other type of variables on the right side. So you separate them out on the left and right side of the equation. So for instance, we would have everything with y on the left, everything with x on the right. So the trick with working with this specific differential equation by using the separation of variables method is that you have to realize that this differential equation is homogeneous. And what that means is that if we had some, well, actually, I'll write it below it. So what this means is that if we set the right side where the variables actually occur of y and x, if we write that right side as some function that contains x and y, so this would be f of x and y is equal to 1 plus y squared over x squared. And let's just rewrite this y squared x squared portion as this, y over x squared. So this would be homogeneous if this equation would remain exactly the same if I multiply my x and y variables by some other variable. Let's just call it t. Some value, some variable, it does not matter. So does this original one equal this new one when I multiply everything by x and y by t? Well, if I do this, this is what happens with this new one. It's 1 plus t times y over t times x squared. Well, what happens to t in this portion? The t's will drop out and they will cancel. So what that means is that the original is going to be equal to the new one no matter what that variable is. So that means that I have a homogeneous differential equation and it can be solved by using substitution. And when I say by using substitution, I mean a lot of substitution. We're going to be substituting a lot. So let's start with our very first one here. So what I'm going to do is I'm going to set y is equal to u times x. Well, why did I do that? Well, that means that u is equal to y over x. Well, look what we have here. Well, let's go ahead and plug that u value in for y over x. So what this means is that my differential equation from up here becomes this. And let me start changing colors here. So we're going to have dy over dx is equal to 1 plus u squared. So let's get rid of the division of dx here and let's throw it on the right side of the equation. So multiply everything through by dx and we end up with dy is equal to 1 plus u squared dx. Well, we have three variables in there now. We have a y, a u, and an x. So we kind of made it more complicated, right? Well, let's start doing one of our first substitutions here. And I'm going to do this one in blue. So we have y is equal to ux. So what is dy equal to? Well, we're going to have to use the product rule for y equals ux in order to get the derivative of y. So using the derivative and using the product rule here, which essentially the product rule written out in variable format is this. Of course, the variables do not directly line up, so you have to do a lot of substitution here, but it's something like this where you have your original f. If you had some kind of function that is equal to fg or fg, and you're taking the derivative of that, you would take the original untouched, multiplied by the derivative of the second one, plus the first one untouched, or the second one untouched multiplied by the derivative of the first one. So essentially what we would have here is that we would have u dx plus x du. And that's what dy would be equal to. So what I can do is now I can plug this down here. So let's go ahead and plug that in for dy. So we would end up with u dx plus x du is equal to, if we take the dx through, we would have dx plus u squared dx. Alrighty, so now let's do some rearranging, because once again, remember, we're trying to separate the variables. And now we have everything in terms of two variables, x and u. So let's separate them out. Let's try to get all our u's and everything involving u on the left side and everything with x on the right side. So doing some rearranging here, this is what we're going to end up with. We're going to end up with x du is equal to dx plus u squared dx minus u dx. Well, we end up with x du, and this becomes u squared minus u plus 1 dx. So fully separating the variables, I'm going to switch this portion right here with the u's and the x's, so switch them, and we end up with this. We end up with du divided by u squared minus u plus 1 is equal to dx over x. So now that I have my variables completely separated, all the u's on the left side, all the x's on the right side, I can finally integrate this sucker. But guess what? It's not going to be easy because this left side. Well, if we integrate both sides, the right side's pretty simple. The right side, if you integrate this, because essentially what this is equal to is 1 over x dx on the right side. Well, 1 over x integrated gives you the natural log of x. And I'm just going to add my constant here on the right side. Technically, both sides will receive an integration constant, but since it's just a constant, some value, I'm just going to leave it on the right side over here. So essentially what I have here is this 1 over u squared minus u plus 1 du is equal to the natural log of x plus my constant. So let's work on integrating this left side, and we're going to come back to here. So let's start working on this left side integration. And I'm going to scroll back up here. And this is where we're going to have to eventually do more substitution. So integrating this left side, and let's focus on the denominator. So we have u squared minus u plus 1. So let's complete the square here. And I'm using quotations in here for completing the square because it's not a full completion. So what I'm going to do is I'm going to make this equal to u squared minus u plus a quarter plus 3/4, because 1/4 plus 3/4 gives you 1. And you might be asking yourself, what are you doing? Well, you will see the trick here that comes around. So completing the square here, we would have u minus 1/2 squared plus that pesky 3/4 there at the end. Well, how does that help me with my differential equation here with integrating? Because this is now my denominator. Well, we're going to have to make another substitution. So as I said, it's substitution with substitution with substitution. So let's do this. Let's make u minus 1/2 equal to the square root of 3/2 tangent of theta. Holy moly, why did you do that? You're making things more complicated. Well, it may seem more complicated now, but when we get this all plugged back into our integration there, you'll see what happens. So let's make the u minus 1/2 equal to the square root of 3/2 times tangent of theta. So since we are substituting now in a new variable of theta, we have du over here. So what does du equal to? Well, if we take the derivatives of both sides here, u minus 1/2 just becomes du. This right side here of the square root of 3/2, well, that's just your constant. That comes down the same, so square root of 3/2. And what is that of tangent theta? Well, tangent theta will become secant squared theta d theta. All right, we're just getting more complex here, aren't we? We're not getting any better. Well, now what we have going on here is that we have this full situation. So we have a u of minus 1/2 is equal to this, and we have du is equal to this portion right here. So let's plug this of the tangent theta square root of 3/2 back into this equation. So plugging this portion back in, we would end up with the square root of 3/2 tangent of theta. All of that would be squared and then plus 3/4. You can't forget your 3/4 on the side here. So this would just be 3/4 because you square root of 3/2 just becomes 3/4 tangent squared of theta plus 3/4. Oh, well, we're really not getting anywhere here, are we? But yeah, it's just a long path to get to where we need to be. So let's still keep working on the substitution model here. Well, now we have this. This is what would be in our denominator. And this is what would be in our numerator for this integration. Not very nice, right? So let's use a trig identity. And let's try to get rid of the tangent. So using a trig identity as such of 1 plus tangent squared of theta is equal to secant squared of theta. Ah, now you're starting to see something come around here, right? So this is our trig identity. So let's rearrange for tangent squared. So tangent squared of theta is just equal to the secant squared of theta minus 1. All right, so now let's plug this in here and see what happens. Keep in mind, we are still working on our substitution model here. So we would have 3/4 multiplied by the secant squared of theta minus 1 and then plus 3/4. Well, what does this become? This becomes 3/4 secant squared of theta minus off 3/4 plus 3/4. Ah, the 3/4 are now gone. So now we're just left with 3/4 of secant squared of theta. So now let's fully replace our integration on our left side with this as du and this as my u. So, or this portion right here, actually, the u squared minus u plus 1. So this whole left side is now the square root of 3/2 secant squared of theta d theta. That's what du is equal to. At the bottom here, we substituted in u squared minus u plus 1, it became this. Then we threw in the tangent squared, and it became this. Then we threw in the secant squared identity minus 1 into that portion, and then we were left with this. So our entire bottom becomes this portion right here of 3/4 secant squared of theta. And of course, this is equal to the natural log of x plus my constant. Ah, do you see what's going to happen here? The secant squares, they disappear. Secant squared of theta, they cancel each other. So that was the whole reason of doing the tangent theta substitute. Well, what is the square root of 3/2 divided by 3/4? Well, the square root of 3/2 divided by 3/4 just becomes 2 over the square root of 3. So essentially, this whole left side then boils down to a very nice integral of 2 over the square root of 3 d theta, which is, of course, equal to the natural log of x plus c. That is so much easier to work with, right? Yeah, so integrate that. So it's just 2 square roots of 3 times theta, which is now equal to the natural log of x plus your constant c. So we have no more integration going on there. We've completed it. So let's rearrange and solve for theta. So theta will be my square root of 3/2 times the natural log of x plus c, and that's what theta is equal to. But remember, we need to find an equation of what y is equal to. So what did theta equal? Well, back up here, if we scroll back up, we had it like this, where this is what's relating theta and u together. So let's pull that equation down here and work with it. So we have u minus 1/2 is equal to square root of 3 over 2 tangent of theta. That's our relation between theta and u. And of course, we can use u to get back to y. So utilizing this theta right here, this theta from this equation is equal to the tangent inverse of 2u minus 1 over the square root of 3. So let's plug that into our previous equation up here. And this is what we end up with. We end up with the tangent inverse of 2u minus 1 over the square root of 3 is equal to the square root of 3 over 2 multiplied by the natural log of x plus my constant c. So what I'm going to have to do now is I'm going to have to get u is equal to what? And then I can substitute in my y for u, or the relationship between y and u, and I can finally get my equation in terms of y. So let's solve this bad boy in terms of u. So we end up with 2u minus 1 over the square root of 3 is equal to the tangent inverse of, or not the tangent inverse, the tangent, because we already have the tangent inverse on this side. So it'd be the square root of 3 over 2 times the natural log of x plus your constant c. There's a lot of room for error and mistakes here, just like that little slip up that almost occurred. So let's get it in terms of u. So then u would be equal to the square root of 3 over 2 times the tangent of all that junk again of square root of 3 over 2 times the natural log of x plus c, and then all of that plus the 1/2. Because the 2 is multiplied by 2. So that's my u equation. Well, what does u really equal to in terms of y and x? Well, remember from our very first substitution, if we scroll all the way back up, here it is. U is equal to y over x. So we will just plug in y over x here for u, and we end up with this, y over x. And I don't know why that y is so weird looking, but that's a y, is equal to all of this. I'm not going to rewrite it. So what we can do is just multiply through by x, and we end up with our final y equation with a constant variable. So y would be equal to x square roots of 3 over 2 times the tangent of the square root of 3 over 2 times the natural log of x plus c, and then plus x over 2. Alrighty, so that is our beginning of our y equation, but it's not our full y equation. Why? WHY is because we have that constant c. So how are we going to find that constant c? Well, we were told a boundary condition at the very beginning. We were told that y of 1 is equal to 0. So what this means is that y will be 0 when x is 1. So what we're going to do is that we are going to plug in x equal to 1 here and y equal to 0 and solve for c. As I said, this is the longest part of this problem, is just getting this y equation. So plugging in 0 for y and then 1 for x. This is what we end up with right here. Square root of 3 over 2 natural log of 1. Oop. Give me my eraser, thank you. Plus my constant c, all that plus 1/2 here. All right, so let's do some algebra here and start solving for this constant c. So we end up with minus 1/2 on the left side is equal to the square root of 3 over 2 tangent of the square root of 3 over 2. Natural log of 1 is just 0 plus my constant. So if we multiply by 2 to get rid of the 2 on this side, we end up with minus 1 is equal to the square root of 3 times the tangent, and if we rearrange inside here, we have c square root of 3 over 2. Getting a little bit easier to work with. So let's take division of square root of 3 to the left, and then the tangent inverse to the left. So we would have tangent inverse of -1 over the square root of 3 is equal to c square root of 3 over 2. And this is where you have to realize that your calculators are going to have to be in radians mode if you want this equation to work out. It cannot be in degree mode. Now, before, with the beginning of this problem, we were working with degrees when we found that alpha angle. But utilizing this equation, we're going to have to be in radians here. So this portion right here, when you take the tangent inverse of this, which I should highlight all of it, gives you a -30 degrees. But we're going to have to be working in radians in here to make everything a distance and make everything possible. So -30 degrees gives us a minus pi over 6 when you convert it into radians. So what I have going on here is my tangent inverse of -1 over the square root of 3 in radian form becomes minus pi over 6 is equal to c square roots of 3 over 2. So essentially my c pops out to be minus pi over 6 times 2 over the square root of 3, which comes out to be minus pi over 3 square roots of 3. Oh my goodness, we're almost there. So my full, intact, complete y equation, which represents the curve of this overall red line that is appearing, is x times the square root of 3 over 2 times the tangent of a bunch of junk, which is the square root of 3 over 2 times the natural log of x minus pi divided by the 3 square roots of 3, close off your brackets, plus x over 2. That is my y equation. Now, there are multiple ways that you can check to make sure this is true. What you can do is you can take this y equation and plug it back into your original differential equation form, which is all the way up here. So that means you would have to find the derivative of that y equation. Oh, yay, let's not do that. But if you were to do that, you would see that this y equation is correct. And another way that you can also check to make sure that it is good is that it states in the problem here that when you're at point B, y equals 0. So when you plug in the distance from A to B, which I believe is like 37 something, when you plug that in, your y equation should be popping out to be 0. So when you plug this in into that y equation, it should pop out to be 0. And it does. So that's another way that you can check to make sure that you've done everything correctly before moving on to your final answer. So that's the reason why I found AB, and that's the reason why I said I would use it later. So if you were to plug in the 37.61967, you would see that y would be 0 for this equation. So let me scroll all the way back down here. So what I'm looking for here is plugging in my overall diameter of that semicircle to see what y would pop out to be at point F. So I'm going to plug in x equal to 150 millimeters, which was the distance all the way from point A to point C, which is the location of where I want my y. Just make sure that your calculators, once again, are in radians mode for this equation. So when you plug in 150 millimeters into this equation at all the x locations, this y will pop out to be 178.7964 millimeters. So that is the overall height of my rectangle, since that diameter of the circle A to C is representing y equal to 0. So F to C will be this y value of 178.7964. So this represents FC. So now that I have FC, after this extremely long process, that is the height of my rectangle. So I can get the area of my rectangle, which the rectangle is fully intact with blue, so we don't have to subtract anything out from it. So it will be this value of my height, which is 178.7964, multiplied by the width of BC, which BC was 112.38033. And this gives me an overall area of 20,093.19 millimeters squared. So That is not the answer. That is just the partial answer. What I'm going to have to do is scroll back up here and find out the other portion that was in blue for the portion of blue in the side of the semicircle, which was 3,959.164. So I'm going to take that number and add it to the area that I just found. And that would give me my total area in blue and thus completing this problem. So total area in blue would be the 20,093.19 for the rectangle plus 3,959.164 millimeters squared that we found for the portions of the semicircle in blue. And this gives us a total of 24,052.354 millimeters squared. And that is our final answer, our total area. Whew, and that's how you would work that particular problem, being that the differential equation was the longest portion. So I hope you enjoyed this video, and I hope you learned a new math skill from it. And if you want to test your abilities even further, please check out the other videos on our channel, as I believe this was the 27th part. Yes, this was the 27th part in this series. And we also have other videos on the channel, especially ones going over differential equations. We also have a video going over this specific differential equation, how to do the checking portion, which is the dy dx portion of that check. If you want to check that out, go ahead. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all that does help us out. Thank you for watching, and I hope you have a fantastic day.